All right, so it's my great pleasure to have Stephan Mandt today to talk with us about the practical and efficient neural data compression. So Stephan is an associate professor of computer science and statistics at UCI, University of California, Irvine. So before he joined the UCI, he was a senior researcher and the head of machine learning group at Disney Research, where that is the place that I first met Stephan. So yeah, he has done a lot of very interesting and exciting work around statistical machine learning and also probability modeling. And recently, he has been, leading the research in this neural data compression that applies generative models for compressing images and videos. So yeah, so welcome. So just take it away.
Yeah, thank you, Ying Zheng. Very nice to invite me, and hi everyone. Yeah, so the title of my talk, as Ying Zheng already announced, is towards practical and efficient neural data compression. And what I'm planning to do today is to give you sort of an unbiased view of the field as much as I can. And at the same time, I'll also kind of tell this in the order in which I personally got excited and invested into this field. So I will start with, how I initially got excited and entering it from the Bayesian machine learning perspective, and how, to me, this field opens up many possibilities, in particular to probabilistic machine learning. I will then talk a little bit about the challenges that the field is currently facing, and sort of an optimistic view of possible future research. All right. Maybe kind of a brief motivation here. Everyone knows that our data is basically exploding. The data globally grows at an exponential rate, and we produce many different types of data. Ranging from video to healthcare data to edge computing, or data arising in decentralized machine learning, and all of these different types, of course, produce massive storage requirements. And on the other hand, besides just more data, we also face new types of data. For example, video, LiDAR data, VR content data, MRI data, or data arising, for example, in climate contexts. And of course, for some of these new data types, there are currently no established compression methods available, making sort of learnable compression highly desirable. So let me give you a couple of examples just to motivate this a little bit more. So to start with, let's take, for example, a look at video transmission and streaming. So, obviously on the internet, there's a lot of videos. Videos take into account about 80% of consumer internet traffic. So only kind of small changes in the efficiency of compressing video will have enormous consequences. But at the same time, there is also fairly specialized video, for example, video conferencing, as we currently do here. And this video has, of course, a much lower entropy than a generic video, right? So we could potentially take a compression algorithm and fine-tune it or specialize it for that particular type of video. And this way, we can realize enormous compression gains. And in fact, this has recently been shown by different groups here. Here you see results from NVIDIA that showed that without realizable quality loss, you can actually get a factor of 10 of bandwidth savings by having a specialized video conferencing compression algorithm. And there's another example of a new type of data, or at least a type of data that's growing in importance. Take LiDAR. So this picture here shows LiDAR data taken in the context of self-driving cars that are recording these data massively. And so typically these LiDAR data sets consist of point clouds involving several billions, or sometimes even up to tens or hundreds of billions of points. For example, there are also LiDAR data showing sort of the entire Sierra Nevada up to the tree level, or in more detail. And of course, we need dedicated compression methods also for those data. Okay. Good. So before I get into the technical details, I want to get everyone on the same page and spend a few minutes on covering the basics of lossy and lossless compression. And so what do we do again as a reminder in lossless compression? So let's imagine that we have data points A, B, and C, and they're living on in 2 dimensions on a 2-dimensional grid here, for example. These could be RGB values of discretized images. And now the first thing that we do is we need a probability model, right? We need to assign probabilities to every lattice point in the grid. And with the help of that probability model, capital P, we then evaluate log probabilities of these different data points. And then we feed these log probabilities into a coding algorithm that will assign bit strings to these log probabilities and the individual data instances in such a way that if like a probability is large, like in other words, a data point is frequent, you will have a short description in binary bit strings. And if something is rare, then you can assign a longer bit string to that, so as to overall minimize the expected code word length. And importantly, this is of course completely lossless, and you can go back and forth in this pipeline. Now, how does practical lossy compression look like? Well, as the name is already telling us, like lossy compression typically amounts to also having a quality loss reduction at some point. And this typically amounts to some sort of rounding or truncation step. So here I introduce lossy compression as a type of rounding. And typically we go from some continuous space into a discrete space, right? And so this is shown here where you have your continuous probability model, and then you sort of take arbitrary points in this two-dimensional space and round it to the nearest lattice. And at the same time, you also do something to your probability model. And we'll cover that the details of that later. And now there's one particular type of lossy compression algorithm, which is particularly important, and that's called transform coding. So the idea of transform coding is that instead of doing the rounding and truncation and entropy coding steps all in the original data space, you actually take your data first and map them into a so-called latent space. And in this latent space, you do the rounding and the entropy coding. And so ultimately, when you decompress the data, you actually map it back into the data space itself. So when we give names to these spaces or letters, then we would refer to the data in the data space as X and the latent space as Z space. And with X hat, we typically denote the reconstructed data. And of course, this looks very much like an autoencoder for those doing machine learning, and we'll exactly draw on this analogy in a few minutes. Now, finally, how do we evaluate lossy compression? Well, we typically look at two quantities, rate and distortion. Rate just indicates the expected average file size of our data set under a certain data compression algorithm. And the distortion refers to the average mean squared error between the reconstructed images and the original images. Or more generally, a distortion measure can be also defined differently, but here, for now, it's useful to think of as distortion of mean squared error. And how do we quantify the difference between different algorithms? Well, imagine you have two different algorithms. First of all, every setting of the algorithm will produce a different point on this rate distortion plane. And if you connect all of these points, you will get a rate distortion curve, which really characterizes all the different settings of the compression algorithm. And when you compare different compression algorithms, we basically want to be in the very bottom left corner, because that's exactly the point which has low distortion and low bit rates. But as we'll learn later, this is fundamentally impossible. So there are always trade-offs between these two different quantities. Okay. So let's go to the important question back of how can we actually learn compression algorithms in an end-to-end way from data? And what would be the corresponding loss function for that? So the first thing to think about is, why don't we start with transform coding? And we now parameterize these encoder and decoder transforms F and G by neural networks so that we can ultimately optimize their parameters. And the loss function that we would ideally like to optimize is then written as follows. We have an expectation under our data distribution. And then the first term is the negative log discrete probability of our rounded encoded data points. That's our bit rate. And then we have plus lambda, like a weighting factor, times another term, which is the expected distortion. Right? It's the mean squared error between the data points X and the encoded, rounded, and decoded data, the X hat. Right? And you can think of that as basically a Markov chain shown on the top right, where we go, again, from data X using F into Z space, then we round, then we evaluate probabilities, and then with G, we go back into data space. Now, what's the problem with that loss function? The problem is we cannot straightforwardly minimize this for two reasons. First of all, quantization or rounding is not a differentiable operation, right? And second, the probability density, P, is actually really a discrete probability. Sorry, it's actually a probability that lives on lattice points. It's not a probability density. and the input is discrete, so we cannot easily optimize that probability with respect to its discrete input. Now, there's one proposed approach that's been very popular by Johannes Ballet and al, and has been since then been widely adopted in the literature. And the idea is to essentially replace rounding by additive uniform noise. So during training, you take our latent state Z and we inject noise, or we add noise into this. And the noise is taken from a uniform distribution centered around 0 and with 1. And the idea is that this uniform noise injection essentially simulates the discretization operation during training. Or to be more precise, it's the model assumption behind that is that essentially the residuals that you obtain by rounding your continuous data to discrete, that those residuals essentially follow this uniform distribution, right? How to deal with these probability densities? Well, one workaround is to actually just relax them to continuous, right? To kind of essentially establish a probability density function, small p twiddle, and once we've learned that, which is easier because it lives in continuous space, we can then just integrate it up and to obtain like a discrete probability mass function. So that's the main idea. Now, if we combine these two ideas, we arrive at the following objective function that we can now optimize using stochastic gradient descent. It's basically a version of what we see above. Again, the difference is that we replaced rounding by noise injection. We relaxed the probability mass function by probability density. And those are the two main changes. Now, for those of you who work with latent variable models, and in particular variational autoencoders, this might look very, very familiar. And so let me actually establish this connection in more mathematical detail. In particular, let's look at variational autoencoders for now. So what again is a variational autoencoder? So it corresponds to a certain, operational diagram where, first of all, you have an encoder that takes data X, puts that into a mapping F to obtain like a mean encoding Z. And ultimately, we inject noise onto that mean encoding to get a random variable Z twiddle. Right, and so that's, you can think of as samples from a conditional distribution, Q of Z twiddle given X, which we use as our variational encoder or variational posterior. Right? So in this case, we choose a uniform distribution, and so then the variational posterior is a box-shaped distribution. Now let's look at the decoder or the generative process of the VAE. So here we sample from our prior P twiddle of Z, and then we take these samples, plug them into a decoder G, to get a mean decoding. And then ultimately in the last step, we add a little bit of Gaussian noise with standard deviation epsilon, right? So that then corresponds, again, to a Gaussian decoder. Let's put it all together and write down the variational bound that we actually optimize when we optimize the variational autoencoder. Following variational inference, which I don't really have a lot of time to talk about, but it's basically an approximation to Bayesian inference. We have a lower bound to the log marginal likelihood. And this lower bound consists of these three terms. We have an expectation of the log prior, of the log likelihood, and the log approximate posterior. And the first important observation is that because the log posterior is actually a box-shaped distribution, it falls away, right? It has it values to 0. And what remains is, after we apply the so-called reparameterization trick, is actually a loss function that is exactly 100% identical to what I just had on the previous slide. Now, for our Bayesian, this is really exciting. It basically means that the image compression community has developed methods that are identical to the tools that are already very familiar with in the variational inference community. And so the obvious question then is, can we maybe borrow from ideas that were already established in variational inference and transfer them to image compression such that we can realize gains that have been perhaps untapped so far. And this is pretty much my personal story. So, I started working with variational inference a long time ago. And actually here on the slide, you see work by Ying Zhang that we did together a long time ago, 5 years ago, when she was working. Oh, and I just realized it should be Li and Mandt. I'm really sorry about that, Ying Zhang.
No problem, no worries.
Proper credits, all credits are to Ying Zhang. So what we did back then is we looked at disentangled representation learning. So we looked at little simple video clips And the question that we asked is, can we learn a probability model that would disentangle content in this video from dynamics in this video in such a way that we could do control generation, right? For example, we could fix the content, the appearance of something, and then we could sample different dynamics, or we could fix the dynamics and sample different appearances. And that was a somewhat successful model back then. And of course, there's been lots of development afterwards, but in some sense, very foundational work. And the first thing we did, when I learned about this compression connection, was then to take this model and convert it into a video codec. Right? The idea being that it might be a very good idea to separate content from dynamics in short video clips. And basically, long story short, as you see a little operational diagram on the bottom, which borrows exactly on this idea that we previously developed in the context of variational inference. Now, I don't want to talk about this particular video compression approach too much. It was one of the first. I think it was paper number 3 or 4 among all learned video compression models. But we kept working on this, and it got way better results, which are more interesting nowadays. So here, for example, is a more recent result from 2021. So the idea here is we took a neural video compression model, and again, by borrowing ideas from generative modeling and variational inference, we did all sorts of refinements on architectures, on priors, to ultimately get better rate and distortion. So in particular, we introduced autoregressive priors. We introduced some kind of structured variational inference and ideas like that, and ultimately got a state-of-the-art performance on neural compression. Pause here for a moment. Okay, so this is the exciting part. Now let's get a little bit more realistic. So let's get a step back from the research and consider the state of the art of the field in 2023. So where are we at the moment? So the good news is that neural compression has met steady gains, and it's already better than classical compression in terms of rate and distortion performance. So let's actually look at different proposed neural compression models and plot them on one particular data set. So here's the so-called codec data set. And what you see here is basically a rate distortion plot, but it's not really rate and distortion, but it's more like quality and distortion. So on the vertical axis, we have PSNR, which is related to mean squared error, but essentially inverse. So it's higher is better. So higher qualities are clearly desired. And on the x-axis, we have the bit rate, right? And also in the bit rate case, we want to be as low as possible, right? And so you see the trade-off that if you have more expensive codes or longer bit strings, then of course your quality goes up. But ideally, you want to have both small bit, short bit strings and also high quality. So we want to be in the top left corner. But what you also see is that there's been a lot of recent development on different people developing neural compression approaches. And you see that these lines, these different rate distortion curves, are basically getting closer and closer to each other. So there's been, in some sense, diminishing returns in the field, which is quite concerning if you think about it. And one immediate question that comes to mind is that perhaps because we've already hit a fundamental performance limit, right? I mean, have we already reached a point beyond which we simply cannot get better in compressing our data? And the unfortunate answer is that such a fundamental quantity exists, and it's called the information rate distortion function. So the question is, are we already hitting the information rate distortion function, which would be very bad news for that particular kind of research. So let's try to address this question in the next few minutes. But before we get there, I want to first of all reveal another sort of not quite as optimistic result about neural compression. Namely, here's a slide borrowed by Google, by David Minnen. What David and his colleagues did is they looked at different neural codecs. And instead of plotting them in terms of rate and distortion, they basically fixed the bit rate. So they looked for parameter settings that resulted in the same bit rate. And then they compared computation and distortion, or better to say quality versus flops, right? So it's quite intuitive that if you have a more expensive algorithm, that you could potentially get better results. And this is exactly what the plot shows you, right? I mean, if you're willing to invest more flops, then the quality goes up. But ideally, you want to have a cheap decoder. So you want to be on the left-hand side, few flops, while also having high quality. So again, you want to be in the in the top left corner. But first of all, the one thing which is maybe obvious is that this trade-off exists, and the neural methods are already way better than sort of BPG, which is a fairly competitive baseline in terms of classical compression. But maybe the not so good methods is when you take into account how long these codecs really take to decode an image. So here, for example, a so-called hyperprior model, which is a fairly popular, not the most expensive one, but a fairly powerful neural compression approach, takes about like 200 milliseconds to decompress an image. And if you, of course, go to these sort of even better models, for those they didn't have the flops, that's what they called, that's what they were drawn as dashed lines. They can actually take up to a minute to decode an image, which is probably intolerably slow, right? Now, the concerning part is there's a new compression method, which is classical, called VTM. And that's actually relatively fast, right? It takes only 77 milliseconds while having also a high PSNR value at that particular bit rate, right? So I'm not saying that this is really a catastrophical result. I mean, there are other downsides that this algorithm has. For example, it takes really long time to encode images, but it at least tells us that we have like some serious competition here in the field with classical methods, and it's not easy to actually, or at least it's becoming more and more apparent that making neural compression faster is probably going to be the next frontier, as opposed to only paying attention to rate and distortion. Okay, so maybe let's first of all summarize these sobering results. I don't know if you know the HBO show Silicon Valley, which is about a fictitious compression startup, and Richard Hendricks is the founder, so it's kind of a comedy show, and he looks disappointed here. So the sobering results are that neural compression are currently in order of magnitude too slow to be competitive with classical codecs. So really have to work hard on making them more efficient. We also see diminishing returns as we walk towards, as we focus more and more on only rate and distortion performance. And of course, there are various other obstacles as well, which we didn't talk about. It might be difficult to define a coding standard. There's certainly some resistance in the industry to change a running system, and some other aspects that we don't have time to discuss here. However, I still want to take a closer look and basically ask the question as, are things really as bad as they seem from what I showed you, right? And so let's actually take these 2 points into closer consideration, in particular the question of whether we've already reached optimality, and the question of how can we make these algorithms faster. First, I want to take a closer look at this rate and distortion function. And to this end, we really need to look at the information rate distortion function. And I need to tell you very briefly on how it is defined. So, first of all, what does it actually do? So basically, the rate distortion function, it's a property only of your data set and a property of your distortion measure. So mean squared error and your data set. No algorithm, no neural networks, nothing. And what it tells you is it's basically telling you something about the lossy compressibility of that particular data set. So you can think of this almost as an extension of entropy, which tells you something about the lossless compressibility of a data set. So, taking sort of a certain level of distortion tolerance into account. So the mathematical definition is written down here. It's a little complicated. It's defined by a mutual information between input and output. And then you're minimizing that expression subject to its constraint. And then you have a stochastic encoder, Q of y given x. And that has to satisfy ultimately that the distortion between input and output has to be lesser or equal than a certain distortion tolerance level d. Right? Now, as you can already guess, this looks fairly complicated. And in the most case, this does not have an easy analytic solution. But before we get there, let me first show you a little drawing, what it really does. So, so what it's helping you to do is it's essentially dividing the plane between rate and distortion into two regions. One region where codecs are feasible and one regions where codecs are not feasible. So for example, the pair of D1 and R1 would be realizable by a codec, whereas the pair D2 and R2 would be not realizable in general by any codec, right? So it can really say for certain that this is impossible here. yeah, so as I already mentioned, is that this has not an easy analytic form, except that, you know, when the data source is Gaussian, which is a very traditional way of looking at it, then you can kind of derive certain things. But as soon as you deviate from Gaussianity, you're basically lost, right? And you have to resort to numerical methods, and even those numerical methods are really limited, as I'll show you in a second.
So Stephan, so there is a question in the chat. Okay, so Harrison asked, do trained compressors work in general for any kind of data set, or only on the family of data sets it is trained on?
That's a great question. Let me actually perhaps get back to that later, but the main idea is that you know, once you train a compressor on one data set, which is sort of diverse enough that it will hopefully generalize easy to other data sets, and that relates to this sort of out of distribution robustness, which I'm happy to talk about more. Yeah, short story is there can be more work on this, but I'm sort of being optimistic in the sense that, you know, when we test these algorithms, we already test them on out of distribution data. So we train them on one data set, and we always test them on other data sets. So we don't just do the random splits. And but yeah, kind of robustness could be an issue. Yeah.
Okay.
Thanks. All right. Okay, so that's the rate distortion function. If we cannot compute it, what can we do else? Well, we can bound it from both sides potentially, right? And this is essentially what we did like a year ago in our ICLR paper that I'm going to talk about later. We introduced upper and lower bounds in trying to sandwich this rate distortion function. Now, what's the meaning of these upper and lower bounds again? Well, the meaning of the upper bound, you can think of this as an existence result, right? Anything that's bounded to the top right of this upper bound should be feasible to compress, right? We've basically an empirical proof that it should be feasible to compress this. Whereas everything that's in the bottom left region of the red curve is shown to be impossible to compress, right? So that's sort of a negative result, or we can never enter that region, right? So that's the meaning of these upper and lower bounds. And both are useful, of course, in compression research, because we can use the upper bounds to essentially assess, you know, whether there are certain guaranteed gains that we should be still able to harvest. And we can use the upper bound in order to essentially say, okay, we're too close to the lower bound, so we should better give up and focus on other things. Okay. All right. Okay, so let me spend a minute or so on each of these upper and lower bounds. So the first result sounds very simple, but it's actually non-trivial. Namely, if you take any variational autoencoder and whose log likelihood, P of x given z, is given by the distortion metric of interest. So for example, if you care about mean squared error, then your likelihood model should be a Gaussian. If you care about mean absolute error, then your likelihood model should be a Laplace distribution. If you choose such a BAE, and it can have any network architecture, any latent space, any priors, then it turns out that the rate distortion function of this corresponding beta variational autoencoder, where you up or down weight the entropy term, gives you an upper bound on the information rate distortion function. So in other words, you can train a lot of different VAEs with different architectures and everything, train them, look at their rate distortion function, and then in the end, you take the envelope and you're guaranteed that this resulting envelope of all algorithms and all models will be an upper bound on the rate distortion function. Right? And so for more details, I'll refer to that paper. The other result is even more interesting, but also way more difficult. Namely, we can also derive lower bounds to the rate distortion function. And again, this is very technical. I want to be very brief here, but the main idea is that you essentially make use of Lagrange duality. So you start with that information rate distortion function, you write down its Lagrangian dual. This typically amounts to some maximization problem over infinite dimensional function spaces, right, as shown here. And then you parameterize these functions by neural networks, limiting sort of the search space. And this way you get a lower bound to this quantity, right? And then you try to optimize this resulting loss function end to end. Now, the problem is that there are all sorts of nasty constraints, and I don't really have to go into detail, but it turns out that this quantity is very, very difficult to optimize. And we'll learn about how difficult in the next few minutes. Okay, so let me tell about a couple of experiments. So the first thing that we did is we started with relatively low dimensional data sets. So for example, here's a particle physics data set where we had particles colliding. So you measured, or you would actually look at simulated data, and you were looking at incoming and outcoming momenta, each of which are sort of 4-dimensional. So you get basically a 16-dimensional data set. And as you can imagine, everything is correlated there, right? Because of momentum transfer. And some of these correlations are shown here in the scatter plots on the left-hand side. So it's sort of a non-trivial data set, if you will, in 16 dimensions, highly structured. Now, can you derive the information rate distortion function of that data set? And so let's look at the plot on the right-hand side. So what you see here is, first of all, the dashed dark red curve, which is the lower bound. Then you see the bright red curve, which is the upper bound, and the shaded region in between should contain, according to our theory, should contain the information rate distortion function. Now, to show that this is a non-trivial result, we compare it to sort of a pretty good neurocompression model, Ballet et al. 21. And we see that this operational rate distortion function, so in other words, the rate distortion function of that codec that it actually realizes, is above of our bounds, right? So this means that our bounds are sort of non-trivial. They're in some sense tighter than the upper bounds that any existing codecs will give us. Okay? So that's kind of good news. Now the question is, how good are these upper and lower bounds? Sorry. And to this end, we actually go even to lower dimensions. We look at a 2-dimensional projection. And then we look at a baseline that is established in the information theory community called the Blahoud-Arimoto algorithm. And that's an algorithm that can actually compute the rate distortion function in discrete settings, in discrete spaces. But the problem is that it's actually, its complexity is exponential in the dimension, right? So we can only really evaluate it in very, very low dimensional setups. But here we did, and we saw that this green curve is indeed contained in these 2 bounded regions, which means that the bounds are valid, right? So that's another confirmation that nothing went wrong in this analysis. Okay, let's go a little bit higher in dimension. So here's a speech data set, which is effectively 33-dimensional. And again, we're able to derive upper and lower bounds, compute them. And again, they're not trivial because the actual compression algorithms are still above of the upper bounds that we derived. So that's good. We can also look at GAN-generated images, which is sort of nice because they give us a controlled way of controlling the intrinsic dimensionality of the data set. So what we did here in particular is we took a trained GAN. We fixed all of the dimensions in the latent space, set them to 0, except for D dimensions. And D could be 2 or 4 in our examples. So, and then we sample from that restricted GAN and generate a whole bunch of training data. And we basically generate a data set that has a true intrinsic dimension of either 2 or 4. Right? In this case, these are all dog images that we generated. And now for these artificially generated data sets, we can basically understand systematically on how robust these upper and lower bounds are upon changing the intrinsic dimension of the data. And long story short, when you compare the left-hand side in 2 dimensions to the right-hand side in 4 dimensions, you see multiple things. On the good news is, the lower bounds, the upper bounds are actually very non-trivial, right? I mean, they're way lower than any existing compression models. Which is a fairly optimistic result, right? So it means that there's a lot to be gained potentially in compressing images using these neural compression models. But then you also see the onset of like almost a negative result, namely you see that the lower bound is actually becoming flatter and flatter as we increase dimensions. And this is actually a known result, as we learned later on, that like these lower bounds to the mutual information are intrinsically difficult to estimate. So we don't have the right tools to reliably estimate these lower bounds in real-world high-dimensional data, right? So that's sort of a negative result coming out of our analysis. But at least, we made progress from, going from a handful of dimensions up to at least 100 dimension, right, with that kind of analysis. But not yet to the millions of dimensions that real-world images would demand. Okay.
Can I ask a question?
Yes, please.
Hi. So, okay, so the way you propose this upper bound, right, is by training a series of different beta VAEs with different beta values, right? So
That's correct.
Okay, so it seems to me that each of these trained beta VAE can provide you a corresponding sort of like compression method, right? So that seems to me is still like you're trying to push the machine learning model to the extreme to see whether you have got the sort of like the limits, right? I think this is still like going back to your previous argument that okay, you want to know whether we have got to the limits, whether we are sort of like still worth doing this experiment. But this seems to suggest that okay, beta VAE is already good enough.
Yeah, so good question, good comment. So maybe to your first comment, if I understood you correctly, you said basically, if we train a beta VAE to get a bound to the rate distortion function, doesn't that automatically already give us a compression algorithm at that rate and distortion?
Yeah,
right?
That's the question.
Isn't that already a real? But the thing is, the answer is no, because you cannot straightforwardly compress data with a simple VAE. You need to kind of work with these very specific VAEs that are highlighted before that are actually discretization, that do discretization. Right? So
I see.
Okay. So, right. So that's the point, right? You need a discrete latent space. And therefore we work with these box-shaped variational posteriors that simulate the rounding operation at training. So not every variational autoencoder gives you a viable codec. Yeah. But on the other hand, like the VAEs are in some sense like a more expressive family of models, and therefore they can potentially get tighter bounds than any realizable codec. So that's the idea. Yeah.
Okay. Sounds interesting. Yeah.
All right. Okay, great. All right, so let's get back to our original question. Are we approaching optimality already? And let's actually look at this plot again. So I told you earlier that there's this fundamental rate distortion function that we don't know where it is, right? And that sort of separates regions that are tractable from regions that are intractable. Now, the bad news is that we couldn't reliably get a bound on the impossible side. So that used to be a lower bound of the rate distortion function, but here in the quality bitrate, it would be actually an upper bound to this rate distortion function. So we don't have that. What we did have is essentially a possibility result, right? We had in this case, a lower bound to that quality rate function. And this basically tells us that it should be possible to find models that realize at least 1 decibel of additional compression gains, right, in this setup. And if we could improve our bounds, it would, maybe prove even more, right, that it's potentially even more possible than 1 decibel, right? So that's basically like we consider this to be like a first step towards bounding these rate distortion functions to really see if we can already, tell upfront for a given data set if it's worth or not kind of improving our algorithms. Yeah, so the other direction still doesn't exist, and you can think of that as either a negative result or a positive result. It's a negative result in the sense that we didn't really achieve to scalably bound the lower bound of the rate distortion function, but it's also an optimistic result because it tells us that there's no proof that we are already close to optimality, right? It's potentially still worth trying to improve these methods more and more on this rate and distortion task. Okay, I see there are a bunch of questions. Let me actually suggest if I maybe just continue a few more minutes and then answer the remaining questions at the end. But I really appreciate it. The feedback is really, really great. So what are some possible paths moving forward, right? I mean, how can we make neurocompression more relevant? And one idea that I'm proposing here is to look at asymmetries, right? So think about the following. If you have a streaming service like Netflix, you have potentially maybe tens of thousands or maybe hundreds of thousands of movies, I don't know, maybe much less, but you definitely have millions, if not hundreds of millions of customers that stream a given movie many, many times, right? Or at least like a given movie is watched a lot of times. So what this means is that, you can spend a lot of time encoding that or compressing that particular movie, but decompressing should be really fast, right? If you want to have equally spread resources on encoding and decoding in total. And there are different ways of doing it. One way is to actually go from symmetric encoders to sort of skewed asymmetric encoders that have a very powerful encoder and potentially a very flat or shallow decoder. That would be a change to the architecture. But another change could be, the type of inference that you do. right? I mean, you could go from amortized inference on the left-hand side to some form of iterative inference on the right-hand side to iteratively refine the latent representation. So let me talk a little bit about what I mean by that. So we had a paper 2 years ago at NeurIPS where where we basically took a whole bunch of ideas from variational inference and made them practical in the context of neurocompression. And one idea relates to the well-known amortization gap in variational autoencoders. What the amortization gap basically tells you is that amortized inference, in other words, using a shared encoder across data points, is just a cheap trick of training your variational bounds in a fast and efficient way. But ideally, you would actually, optimize every individual data point's own latent variables directly using gradient descent. But oftentimes, this is sort of too slow to be practical. So this is basically shown on these two plots where we have the global optimum in red. We have the guessed optimum by the inference network in green. But if you can afford to do gradient descent, you can actually get closer to the optimum. So closing this inefficiency in neurocompression can be done by iteratively refining the latent representations of every compressed image, and we'll get to that shortly. There's also another suboptimality called the discretization gap. What is the discretization gap? Well, that's exactly the mismatch between how you train your variational autoencoder loss function, your compressive autoencoder during training by noise injection, but then at test time, when you use it in practice, you replace noise injection by rounding, right? And that's how you evaluate your loss function. So there's a mismatch between how you train the model and how you use the model, and the result of that mismatch is called the discretization gap. Now, this gap, turns out, can be closed by essentially doing a discrete search at test time, right? I give you a new image, you have a trained VAE, and now instead of just taking the output of your encoder, you actually just use that as an initialization point, and then you do a discrete search on the discrete grid space to find a better compressed representation of that image. And when I say discrete search, I of course don't mean that literally, but what you actually do is you do a sort of gradient-based search using the Gumbel softmax trick, which we called Gumbel softmax annealing, which essentially allows you to slowly converge to a point on that discrete space over iterations. So that's approximately 100 times slower than the regular training, but I'll get to that later. It will actually get much better results, as you'll see shortly. Yeah, and I'm gonna skip the last contribution here. So how does this Gumbel softmax annealing work in practice, and how well does it work? So what you see here is a rate savings plot. What this means is that on the x-axis, we have, again, PSNR, different quality levels. And on the vertical axis, we have the savings in bit rate of any of those depicted algorithms relative to a baseline in percent, right? 50 to 20%, for example. And that baseline is that flat line that you see here, which is actually BPG, which is a classical codec. Now, what we did in this work is we took an established neurocompression model, the Brown curve, and then we used these iterative inference ideas at test time only without changing the trained model, right? We only searched for a better representation of that data point. And this way we could actually lift the bit rates of that data point by about, or reduce the bit rate by about 15 to 20% at different quality levels, right? And so this is quite remarkable. You can actually even see that, when you look at a large image and you look into a certain patch of the image, and then you do the iterative latent variable refinement on it, you see that you'll actually find a compressed representation that will capture more details of that given image. Okay. So this is one example of exploiting this asymmetry between encoding and decoding. What else can you do? Another thing is to make coding faster in general, right? And the short answer here is, of course, JPEG is extremely efficient because there's lots of specialized hardware for that. There's been, decades of research going into this. But another reason why JPEG is so efficient is that it actually corresponds to a linear autoencoder. Right? It turns out JPEG is a linear autoencoder. So what you namely do is you kind of take your image, you transform it into these YCC components, then you apply a discrete cosine transform, then you apply a scaling transform, and ultimately you round, right? And all of these steps, except for the rounding, are linear operations. And ultimately, when you then decompress your image, you actually just do these inverse transformations in the reverse order, right? And so basically by drawing on inspiration from these JPEG-like decoders, we can potentially develop learned compression models that are both fast, but still better than these hand-designed codecs. Let me skip that part as well. The last direction that I want to talk about is the idea of perceptual distortions and the importance of perceptual metrics. So it turns out that when we do compression, we basically have different targets in mind. We want to have a low bit rate, we want to have a low distortion, but we also want to have a good perceptual quality. And it turns out that low distortion is actually not the same as good perceptual quality. In fact, many different image transformations can be applied to an image that will result in the same mean squared error, but that have vastly different perceptual qualities. So these images here that you see on the right-hand side are taken from an NYU blog. And what you see here is like, an image of Albert Einstein that is perturbed using different kinds of transformations. Sometimes we just shift the image by a pixel or a few. Sometimes we add salt and pepper noise, or we blur the image, or we sort of compress and decompress it with JPEG. And in this case, all these transformations resulted in exactly the same mean squared error. But as you can see immediately from these results is that some perturbations are barely noticeable. For example, the spatial shift, whereas others are heavily distorting the image, for example, the Gaussian blur. Right? So distortion is not the same as perceptual quality. So then the question is, how can we train a neurocompression model to take more of these perceptual qualities into account, as opposed to naively and only focusing on mean squared error? And again, here I'm reporting essentially by works by Google and others that build up on that. One famous work was called Hi-Fi-C, which the machine learning community would probably call a VGAN or VAE-GAN hybrid model. And the idea is basically relatively simple. You have a variational autoencoder-based compression model, but then in addition, you add another loss term. And this loss term discriminates or tries to identify whether the decompressed image actually is a realistic sample from the data set or not. Right? Can that decompressed image be detected as an outlier from the data set of natural images based on its compression artifacts? Right? So you just add another GAN loss term to that. And if you do that, it turns out you can actually achieve much better perceptual results at the same time, also relatively small bit rates. So what you see here, for example, on the right is a single image divided by half. The left side was compressed and decompressed using Hi-Fi-C. And the right-hand side was compressed and decompressed with JPEG. And what you see is that JPEG not only takes twice as many bits, but also has like a much blurrier reconstruction than this perceptual compression approach. Right, so this is actually a very promising future direction of research and extremely relevant. So going a little bit more into this surprising result that distortion is different from perception. So this has been actually analyzed using really on a theoretical level by Blau and Michaeli. And they not only looked at compression models, but they looked at a broader class of machine learning models. And what they really found was that there's this inherent trade-off between distortion and compression, right? I mean, basically you have these two different terms. On the one hand side, you have a distribution matching term. You want the distribution of reconstructed images to match the data distribution, but then at the same time, for every instance, you want the decompressed instance to resemble the original data point. And those are just two different optimization targets, and there's really a fundamental trade-off between both, right? So if you're more interested in that, I recommend reading up on some of the literature that I'm citing here at the bottom. And the lessons to be learned here is, again, that classical distortion metrics are somewhat misleading, actually. They're highly useful, particularly for developing models and for debugging models, but they should by no means be taken sort of as the only quantity that matters, right? And in particular, these compressive variational autoencoder models, they're directly being optimized towards rate and distortion, where other models that are very promising are not optimized for rate and distortion. And therefore, they might actually get better results than VAE-based compression models. So I'm just talking here about diffusion models and also about these kind of GAN-based hybrid models. And this gets me to the end of my talk. So to summarize, we talked about neurocompression and the upsides and downsides sides of these approaches. And the main message here is that computation aside, neurocodecs are actually better than classical codecs, right? So they get better rate and distortion results. But when we take computation into account, then neurocompression is actually not competitive yet with traditional codecs. So it's basically generally observed that it's very difficult to reduce the flops without sacrificing the rate distortion performance, although there's currently no theory that sort of would support that, that this is not possible in general, right? So it's more like an empirical fact that's being observed. The reason it's currently not widely deployed yet is that it doesn't experience like the 10x gains that deep learning has seen in other fields. And it's hard to say why this is theoretically the case, right? Because information theory only gives us the optimization objectives, but it doesn't give us any recipes on how to actually construct compression algorithms. Now, that said, there could be enormous gains to be harvested as soon as sort of we either move to parameter efficient architectures or if sort of the hardware catches up, right? Because right now the comparisons we did were not really an apples to apples comparison. We compared sort of compression models, classical on CPUs and neural models on GPUs, and you know, ultimately I think there's going to be a lot of hardware improvement to be expected on the neural compression side. And then finally, on the rate distortion and realism front, neural compression does have a very clear advantage over traditional codecs, and that's why a lot of research focuses on this direction. So there's lots of promise, and again, even more when the hardware will catch up, hopefully in a few years. And finally, of course, there's lots of promise if you consider non-traditional data types for which there's simply no competition, right? So you can look at point clouds, you know, 3D data, and many other data types that are just being developed at this point. So with that, I'd like to close. So thank you very much for your attention, and I'm happy to answer all your questions.
All right. So thank you very much for the great talk. Okay, so we do have a few questions, right? So maybe we can first address the question in the chat. And Islam, would you like to clarify your question?
Thank you very much for this fantastic presentation. So I'm not a very expert in the field. I do work on generative models, but primarily on graph representations. A lot of graph data, generating graphs and at different scales across different domains and across time. So I was just, a bit curious about using compression to speed up the training of, for example, graph neural networks. And here you mentioned discretization. So does your model, how do these models generalize, or how do you see them generalize across different scales, for example, or discrete spaces? Like, can you comment a little bit on that?
Yeah, definitely.
Yeah, thank you.
Yeah, thanks for the question. Yeah, first of all, how do these models generalize? So it might be that we were particularly lucky in sort of image compression in the following sense. So it turns out that all of these image compression models are based on convolutional architectures, right? And in particular, they have relatively small convolutions, relatively small receptive fields, which in turn means that the latent spaces that we use are relatively large, and they actually preserve a lot of the spatial locality. If you look at certain channels in the latent space, they look like images, basically, like downscaled images. And what this is, and this is necessary to actually achieve good reconstructions. I think the reason why these models generalize so nicely is that basically the model effectively only extracts information from patch levels, on the patch level, right? Because the convolutional receptive fields are so small. And in fact, actually, if you take a closer look at, what do these convolutional filters actually learn, they learn features that highly resemble these discrete cosine transformations, right? So they're not very semantic. They're more like, very close to the input level. And I think that's the reason why these methods do generalize well. Now, to your question, if you look at other data types, you might run more into these generalization problems, right? I mean, as soon as your compression model becomes more semantic, it might overfit and then sort of assign longer code lengths to out of distribution data. Yeah.
Thank you.
Okay, next question. So Guoxiang, maybe you can unmute yourself.
Yeah. Can you hear me?
Yes.
Yes.
Okay. I'm just a touch confused because I'm sort of struggling to combine my knowledge of VAEs and traditional compression. Is it correct that you sort of in the embedding space or the representation space of the VAE, you use you'll have a probability mass function that you'll have learned, and then you use that and feed that into Huffman coding or arithmetic coding or something to get your actual compression, and then how do you then, and then how is that then trained? Like I understand the reconstruction part. I'm not understanding how you minimize the rate through the Huffman coding step.
Yeah, definitely. Let's see how quickly I can go to previous. Oh yeah, I think I wanted to be here. Yeah, this is basically one slide before. This is basically what I try to say here. So sorry. Yeah. Okay. So basically, you have the following loss function. Ideally, you would like to optimize this, right? You have an encoder f that you use to go from data x to z space. Then you apply rounding, which are the brackets, and then you evaluate your log probability model on that rounded encodings, and that's the term that you would like to minimize, right? Every data point should have like you would like to optimize the entropy model such that it places high probability mass on actually existing data points from your data set. Right. Yeah. So that's what the first term is doing. Then the second term here is this reconstruction term. So you have again expectation under samples from the data, and you just minimize the difference between x and g of x of it should be actually g of rounding of f of x. Sorry about that. Right. Yeah, so this is basically the reconstruction term, right? You encode with f, you round, you decode with g, and the result should be close to x, right? And so that loss function depends on both g and f, right? And so now you just want to train everything end to end, right? And now there are two challenges. One is basically there's only one challenge. How do you deal with the non-differentiability of the discreteness? Right. And there we introduce these two. Okay.
Yeah, I understand. I think the main issue was I was thinking that you were actually doing some sort of bit like coding into bits during the training, but you're just learning some sort of model over a latent space, and then only at evaluation are you using, say, Huffman coding. Well, you use Huffman coding because that's optimal or whatever.
Exactly. The coding scheme itself is optimal. Yeah, the coding scheme is untouched. You only change the probability model. Yeah. Right. You only learn the probability model.
I guess a couple of questions. One, so for lossless compression, then is that just going to be learning the transform, so learning some sort of latent space? Then is that, or do people, because what you've sort of started with lossy compression, which is a bit odd to me.
Yeah, that's true. It's mostly because I did most of my work on lossy, and most people do lossy, but there's also work on lossless compression. And the short answer, what you do there is, well, first of all, you drop the second term, obviously, right? Because there's no transform into a latent space. You directly operate in Z space. So you would have just only the first term, and f of x would be just Z sample from the data distribution, right? You would just like you would only have the first objective term where you basically try to optimize just a log probability model over discrete data. And you can again relax that discrete model to continuous to make it learnable.
And just a couple of questions on I think a more practical side of things. Like you talk a lot about images, and you also mentioned some other data types. Has there been much work in using language models? I think, there's a lot of talk about large language models being good for generation or whatever, but are they good for compression?
Yeah, that's a good question. I know there are some people working on this. It's certainly like a much smaller community. I think Google had some. Certainly, they have a team, and I heard about it, that they basically try to look at language models for lossless compression of text. But it's not yeah, I would say it's a slightly different community, but they might use different methods ultimately. Yeah, I'm not super familiar with that line of research.
Yeah, I guess the final question I ask is like, what are really the most the applications where this could see the best uses? Because you talked before about how in terms of computational cost and as sort of a result, like portability, neural compression isn't great because you're not going to be able to run a neural network on, or at least right now, on every single device that supports images.
Yeah,
it's not going to supersede JPEG anytime soon. So I'm just curious, it's like, what are the, or at least in the sort of shorter term, what are like the most promising applications?
Yeah, those are great questions. Yeah, I mean, first of all, of course, it does supersede JPEG, but there are more competitive models nowadays, like BPG and BTM, which are sort of traditional codecs. But you're generally right. I mean, they're fairly slow. Again, I think it's still, people are still trying to kind of make these codecs more efficient, and this is a fairly recent trend. It has only started, I would say, like a year ago or so, and only a subset of the community is realizing that this is really sort of an important new frontier. So I'm still optimistic that we can actually do better on image compression. The other thing is also, if you focus more on perception, right? I think this is really important. So even with perceptual losses, I think there are lots of gains to be accepted. Maybe the combination of perceptual losses and kind of lightweight architectures could be still very interesting for image compression. Other than that, you know, I think all these new data types, you know, 3D content, for example, for AR, VR, could be very interesting to compress. Also, there's what I didn't talk about is this task-oriented compression line of research, where imagine you have a cell phone and you want to, you know, take a video on the cell phone where you automatically want to segment the video, but you don't have the power to do it on the cell phone. You want to do it on an edge server. So you could compress the whole video, send it to the edge server and do all the machine learning there, but then you have to reconstruct it first and then apply the machine learning. So instead, you can actually just have an end-to-end neural network pipeline that's distributed. The first couple of layers are on your cell phone, then you have a compression layer along with entropy coding, and then you continue the operation basically on the edge server, right? So this task-oriented compression, I think, is already being used in certain applications, and so that might be also very more and more important, because like more and more data is being analyzed by machines as opposed to humans, right? So, yeah.
Yeah, that's actually quite interesting. Or like federated learning, where
exactly,
you could do neural compression of neural network weights for I don't know.
Exactly,
okay.
and there's also gradient. There's also gradient compression, actually using very similar methods in federated learning. Yeah.
Mm-hmm. Thank you very much.
All right. So I think we are out of time, but again, so thanks very much, Stephan, for this very interesting talk. And I think the audience here will definitely learn a lot from this area of research. So thanks again.
Thank you too.